Science has a long history of silencing its boldest thinkers. We are about to explore 33 theories so radical that science journals once banned them outright. This journey uncovers the dangerous ideas that challenged our understanding of everything, from the birth of the cosmos to the nature of reality itself. You will discover why established powers feared these concepts and what their suppression cost human knowledge. We will see how a single rejected idea could have rewritten the laws of physics. This is not just a list of forgotten speculations. It is a story about the courage to question everything. By the end, you will never look at scientific authority the same way again. What happens when the gatekeepers of knowledge decide an idea is too dangerous to exist? A galaxy spins, its arms tracing perfect spirals against the blackness of space. For decades, we have been told this majestic structure is bound by the gravity of a substance we cannot see. Dark matter, an invisible glue holding the cosmos together. But what if the true architect of this cosmic design is not a mysterious, unseen mass, but something far more tangible, a force that powers our very homes? This is the radical proposition of the electric universe theory. It dares to suggest that electromagnetic forces, not gravity, are the primary sculptors of the cosmos. Imagine the universe not as a collection of isolated islands governed by gravity, but as a vast, interconnected circuit, alive with flowing electrical currents on a scale so immense it defies comprehension. This idea was considered so heretical that it was effectively banned from mainstream scientific discourse for challenging the fundamental gravitational dogma of modern cosmology. The theory found a powerful voice in Hans Alfvén, a Nobel Prize-winning plasma physicist. He argued that 99% of the visible universe is made of plasma, a state of matter superheated into a soup of charged particles, and that this plasma naturally forms long, filamentary structures capable of conducting electricity across light years. These cosmic power lines, he proposed, could organize galaxies and power stars with an elegance that gravity alone cannot match. The predictive power of this idea is startling. While standard models require copious amounts of dark matter to explain why the outer arms of galaxies spin as fast as the inner cores, plasma cosmology models can replicate these rotation curves using only the electromagnetic interactions of the visible matter. Furthermore, it reframes solar flares not as mere magnetic explosions, but as colossal electrical discharges, like a cosmic circuit breaker being tripped. Even data from space probes seems to whisper hints of this electrical reality. The Cassini mission detected what some researchers interpret as an electrical current flowing between Saturn and its moon Enceladus, a potential signature of the very circuit-like behavior the theory predicts. So we are left with a profound and unsettling question. What if our entire understanding of gravity, the force we thought defined the universe, is merely a shadow, a local effect of a much deeper and more powerful electromagnetic reality? This challenge to the cosmic order forces us to reconsider everything we thought we knew, leading directly to another cosmological upheaval. But if the cosmos is an eternal electrical circuit, what does that say about its ultimate origin? The dominant story of creation, the Big Bang, tells of a single explosive moment birthing everything from a point of infinite density. Yet for decades, a rival theory offered a vision of breathtaking elegance, a universe with no beginning and no end. This was the steady-state model, and it proposed a cosmos infinite in both time and space. Instead of a dramatic genesis, it suggested that new matter is continuously and quietly created in the voids between galaxies, just enough to maintain a constant density as the universe expands. The theory's most famous champion, Fred Hoyle, famously gave its competitor its name, using the term Big Bang almost mockingly during a radio broadcast to highlight what he saw as its absurdity. He argued for an eternal, self-renewing universe, a concept many found more philosophically satisfying than a sudden beginning from nothing. The steady-state theory's downfall seemed sealed with the accidental discovery of the cosmic microwave background radiation, a faint hiss of energy found everywhere in the sky. This was quickly interpreted as the cooled remnant of the Big Bang's primordial fireball, a relic from a time when the universe was young and hot. Yet even as the Big Bang became orthodoxy, steady-state proponents pointed to lingering mysteries. They questioned the strange uniformity of this background radiation, asking how regions of the universe too far apart to have ever been in contact could have reached the same temperature if they originated from a single, chaotic point. This horizon problem suggests the universe looks the same in all directions not because of a shared origin, but perhaps because of a deeper, more continuous process. The debate forces a critical question. Is the Big Bang an unshakable truth, or simply the most convenient story we have woven from the evidence? This challenge to our understanding of cosmic beginnings inevitably leads us to question the very stage upon which the universe plays out, the nature of space and time themselves. This challenge to the very fabric of space-time brings us to a theory that questions the nature of reality itself. What if the three-dimensional world you experience, the solidity of the floor beneath your feet and the vastness of the night sky, is merely a projection, an elaborate illusion? The holographic principle proposes exactly that. It suggests our universe is akin to a hologram, a three-dimensional image encoded with all its information on a distant, two-dimensional surface. Think of it like a cosmic DVD, where the flat disk contains the complete data for a rich, immersive movie. In this case, the movie is everything we perceive. This mind-bending idea did not come from science fiction, but from the depths of theoretical physics, specifically from trying to understand the most enigmatic objects in the cosmos, black holes. The puzzle was this: what happens to the information about an object when it falls into a black hole? Quantum mechanics states that information can never be truly destroyed, yet black holes seem to obliterate it completely. This is the black hole information paradox. Physicist Leonard Susskind and others found a potential solution by applying the laws of thermodynamics to black holes. Their calculations revealed something astonishing. All the information describing everything within a volume of space could be perfectly encoded on the two-dimensional boundary of that space. The event horizon of a black hole, they argued, acts like that cosmic DVD surface, storing information about everything that has fallen in. The implication is staggering. If this holds true for a black hole, could it be true for the entire universe? The principle suggests that our reality, in all its rich detail, might be a projection from the outer limits of the cosmos. This means the universe has a finite amount of information, a maximum number of pixels, if you will, that define its resolution. While not outright banned, this idea was long dismissed as fringe speculation because it fundamentally demotes our experienced reality to a shadowy byproduct. It turns the universe into a kind of simulation, not necessarily run on a computer, but operating on the profound principle that information is the most fundamental substance of existence. This radical blurring of the line between the real and the informational forces a startling possibility. If our universe is a projection, what or who is projecting it? The answer might lie in a theory that suggests our cosmos is a carefully crafted artifact. If our reality is a holographic projection, then the next logical question is almost terrifyingly simple. Who or what is the projector? This line of thought leads directly to one of the most debated and mind-bending theories of our time, the simulation hypothesis. It proposes that our entire universe, from the most distant quasar to the very feeling of your own consciousness, is not base reality. Instead, it is an elaborate simulation, a kind of ultra-advanced video game running on a computer of such immense power that its nature is beyond our comprehension. For a long time, this was purely the domain of science fiction, a philosophical curiosity that changed significantly with the work of philosophers like Nick Bostrom. He constructed a stark logical argument. If even one advanced civilization ever arises in the cosmos, and if that civilization develops the technology to run detailed simulations of its own history, then the number of simulated minds would quickly and vastly outnumber the one original biological civilization. Statistically, therefore, the odds are overwhelmingly high that we are among the simulated beings, not the original ones. The scientific establishment has largely rejected this idea, not necessarily because it is wrong, but because it is currently untestable. A core tenet of science is that a theory must be falsifiable, meaning there must be a way to prove it wrong. Since we cannot peek outside the simulation to check, many scientists dismiss it as unscientific speculation, a modern form of metaphysics. Yet, a few daring physicists refuse to let the idea go. They search for potential glitches in the fabric of reality, tiny errors or shortcuts that a programmer might have taken. They analyze the cosmic microwave background radiation, looking for repeating patterns or anomalies that might resemble the pixelation of a screen or the code of a computation. The implications, however, stretch far beyond physics. If this is a simulation, what are the ethical rules of our existence? Are our actions our own, or are they predetermined by an algorithm? Does suffering matter less if it is simulated? The theory forces us to confront the very meaning of reality and our place within it. And if life itself is just a sophisticated program, it raises a monumental possibility. Perhaps the code for life is not unique to our planet, but a fundamental part of the cosmic operating system. The idea that life itself could be a form of cosmic programming leads to a startling possibility. What if the blueprint for biology did not originate on our planet at all? This is the theory of Panspermia, but in its most radical form, directed panspermia. It proposes that life on Earth is not a local miracle but a deliberate transplant, a seed sent across the galaxy by an intelligence we have yet to meet. Even the basic version of this idea, that microbial life can hitch a ride on comets and asteroids, was once met with deep skepticism. The directed version, suggesting a purposeful act of cosmic gardening, was treated as outright heresy. Francis Crick, the Nobel laureate who co-discovered the structure of DNA, found the molecule's intricate complexity almost too perfect to be a product of random chemical reactions on a primitive Earth. He openly wondered if such an elegant code could have been designed and dispatched by a civilization far older than our own. The discovery of extremophiles gave this speculation a tangible foundation. We now know life is not the fragile flame we once thought. Microbes thrive in boiling hydrothermal vents, survive the vacuum of space on the outside of the International Space Station, and lie dormant in ancient ice for millions of years. These are not delicate flowers, they are cosmic survivors, perfectly suited for a long journey between the stars. This shifts the fundamental question of life's origin from a where to a who. Are we the product of a lonely, accidental genesis, or are we merely one branch on an immense galactic tree of life, planted by gardeners whose motives we cannot yet fathom? This concept of an external influence shaping our very existence naturally extends to another profound mystery: the power of consciousness to shape the physical world around it. The very act of looking at the universe might be what brings it into being. This is the startling core of the consciousness-created universe theory, a radical interpretation of quantum mechanics that places our minds at the center of cosmic existence. It suggests that reality remains in a blurry state of pure potential, a haze of overlapping possibilities, until a conscious observer makes a measurement. At that moment, the wave function collapses and a single, concrete outcome snaps into focus. This idea, championed by brilliant minds like John von Neumann, was not born from metaphysics but from wrestling with the bizarre results of experiments like the infamous double slit. When particles like electrons are fired at a barrier with two slits, they create an interference pattern on the other side, as if each particle is a wave passing through both slits at once and interacting with itself. But the moment scientists place a detector to see which slit the particle actually goes through, the behavior changes instantly. The wave-like pattern vanishes, and the particle acts like a single, solid object. It is as if the particle knows it is being watched. The mainstream scientific response has been to sideline this mind-bending implication. The popular Copenhagen interpretation essentially says it is pointless to ask what the particle is doing when we are not looking, while the many worlds interpretation proposes that every possible outcome happens in a branching multiverse, a solution some critics call extravagant. But the consciousness-centric view refuses to let the observer off the hook. It dares to propose that consciousness is not a late-arriving guest at the cosmic party, but a fundamental force, as integral to the universe as gravity or electromagnetism. This transforms our role from passive spectators to active participants in an ongoing creation. Are we simply discovering the laws of physics, or are we, through the very act of perception, writing them moment by moment? This profound connection between mind and matter challenges the linear flow of time, suggesting the present moment is not a passive reading of the past but an active act of selection. Your sense of a flowing present moment, that undeniable feeling of now, might be the universe's most convincing illusion. The block universe theory, a direct consequence of Einstein's theory of relativity, proposes a reality where time does not pass at all. Instead, the entire cosmos is a single, frozen, four-dimensional structure, often called a block. In this view, time is simply another dimension, much like length, width, and height. Your birth, your first step, and your final breath are not events that come into being and then vanish. They are permanent fixtures, fixed coordinates in an immense cosmic sculpture. The past is not gone, and the future is not unborn. They are just as real as the city you cannot see from your window right now, but which you know exists. This challenges the very core of human experience. We feel time flowing, but according to this model, that feeling is a trick of consciousness, a mental cursor scanning across a timeline that is already complete. Philosophers have grappled with the chilling implications for free will. If the future is already out there, a destination waiting for us, then are our choices truly our own, or are we just reading from a script we cannot see? The debate is fierce. Some argue that our conscious experience of a moving now is what creates time, making our perception the realest thing there is. Others maintain that the block universe is the true, objective reality, and our fleeting sense of the present is a biological limitation, a necessary illusion for a brain that must process information sequentially. This redefinition of time as a static landscape leads directly to a theory about the ultimate fate of the cosmos, a cycle of cosmic death and rebirth that repeats across eternity. If time is a frozen block, then perhaps the universe itself is caught in an endless loop. The cyclic model proposes a cosmos with no ultimate beginning and no final end, only a perpetual rhythm of cosmic death and rebirth. In this vision, our universe is not the result of a single, unique explosion, but merely the current phase in an infinite cycle. Each cycle begins with a big bang, expands for billions of years, and then, instead of fading into cold darkness, contracts back upon itself in a cataclysmic big crunch. This collapse then becomes the seed for the next big bang, a cosmic phoenix rising from its own ashes. It is a grand, eternal dance of creation and destruction. This idea is a modern incarnation of ancient cosmological views found in Hindu and Buddhist traditions, which speak of vast cycles of time. Yet for much of the 20th century, this elegant concept was pushed to the fringes, overshadowed by the prevailing story of a single, linear Big Bang. The theory found a powerful new voice in physicist Paul Steinhardt, who helped develop an ekpyrotic model, from the Greek word for conflagration. This version suggests our universe exists on a three-dimensional membrane, or brane, floating in a higher dimensional space. A Big Bang, in this view, is not a singularity but a collision, a dramatic event triggered when our brain smashes into another. This elegantly sidesteps the profound metaphysical problem of something emerging from nothing, replacing a mysterious singularity with a physical, if extraordinary, event. The search for evidence turns to the oldest light we can see, the cosmic microwave background. Proponents of the cyclic model argue that the detailed pattern of this radiation, the faint echo of the universe's birth, might contain subtle imprints or scars from the universe that existed before our own. These would be faint whispers of a previous cosmic cycle, a pattern within the static. Is our universe, then, just one chapter in an infinite cosmic book, with an uncountable number of stories already told and countless more to be written? This view of an eternal, repetitive cosmos stands in stark contrast to a theory that suggests our universe is anything but ordinary, that it is, in fact, uniquely and miraculously fine-tuned for our existence. Against the backdrop of an eternal, cyclic cosmos, our own existence appears impossibly fragile. The universe's fundamental settings are not arbitrary. The force of gravity, the strength of the nuclear forces, the mass of an electron, each is a dial on a cosmic control panel, and every single one is set to an astonishingly precise value. If gravity were just a fraction stronger, every star would burn through its fuel with ferocious speed, collapsing into black holes long before planets could form or life could stir. If the nuclear forces were slightly weaker, hydrogen would never fuse into helium and the stars themselves would never ignite. The cosmos would be a dark, lifeless void. This incredible precision is known as the fine-tuning problem, and it leads to one of the most controversial ideas in modern science. The strong Anthropic principle makes a staggering claim. It argues that the universe must have these life-permitting properties for the simple and profound reason that we are here to observe it. Our existence is not a lucky accident within a universe that just happens to be suitable. Instead, our presence is the very explanation for why the universe is the way it is. This logic sounds almost circular, but its implications are anything but trivial. It suggests a form of teleology, a purpose or goal written into the fabric of reality from the very beginning. The universe, in this view, seems to have life and consciousness as its ultimate endpoint. For many scientists, this was a step too far. The principle was heavily criticized for venturing into the territory of theology, for smuggling the idea of a creator or a designer back into the sterile halls of physics. Critics argued it was not a scientific explanation at all, but a tautology, a statement that things are the way they are because they could not be otherwise. It was dismissed as an unscientific surrender, an admission that we cannot find a deeper reason. Yet the unsettling question remains. Are we the beneficiaries of the most monumental coincidence in history, a one in a trillion roll of the cosmic dice? Or does our ability to look up at the stars and ask these questions point toward a deeper truth, that the cosmos and consciousness are fundamentally linked? This fine-tuning argument, whether seen as evidence of design or a bizarre fluke, forces a radical shift in perspective. It places life not as a passive byproduct of cosmic evolution, but as its central, defining feature. This vision of a cosmos fine-tuned for life finds a powerful echo much closer to home, not in the distant stars but in the living skin of our own planet. Earth itself appears to behave as a single, vast, self-regulating entity. The Gaia Hypothesis, proposed by scientist James Lovelock, dared to suggest that our world is more than just a planet with life on it. It is a superorganism where the biosphere, the sum of all life, actively works to maintain the conditions necessary for its own survival. Lovelock's insight came from his work with NASA, searching for signs of life on Mars. He realized that a living planet would have an atmosphere far from chemical equilibrium, a persistent instability caused by biological processes. Earth's atmosphere, rich in oxygen alongside reactive methane, is exactly that, a signature of life on a planetary scale. The theory posits that life does not simply adapt to a passive environment of rock and water. Instead, life and its environment are locked in a continuous, co-evolutionary dance. When the sun grew hotter over billions of years, life did not just suffer the increasing heat. According to the Gaia idea, biological processes may have helped regulate the planet's temperature, for instance by drawing down greenhouse gases like carbon dioxide. The salinity of the oceans has remained stable enough for aquatic life for eons, not by chance, but potentially through feedback loops involving salt-loving microbes and geological cycles. Initially, the scientific establishment ridiculed the idea. It sounded less like a hypothesis and more like a New Age fantasy, ascribing a quasi-conscious purpose to the planet. Critics accused Lovelock of teleology, of implying that life had a goal, a notion that clashed fiercely with the neo-Darwinian view of life as a blind, competitive struggle. Yet, the provocative power of Gaia was undeniable. It forced a profound shift in perspective, ultimately sparking the entire field of Earth system science. We now take for granted that living things profoundly shape global cycles, from the oxygen we breathe to the composition of the clouds. So, is Earth alive? Not in the sense of having a mind or intention, but perhaps in the sense of being a complex, integrated system that displays a form of resilience and homeostasis found in all living things. This holistic view of a living planet suggests that life, once it emerges, becomes a powerful geological force, capable of engineering its own destiny. And if life can reshape a world, could it eventually reach beyond it, seeding the cosmos as a natural extension of its will to persist? Our own planet's remarkable self-regulation hints at a universe where life is not a passive accident, but an active, shaping force. But if life is so tenacious, so capable of engineering worlds, then the silence from the cosmos becomes deafening. This is the core of the Fermi paradox, the haunting question posed by physicist Enrico Fermi. If the universe is vast and ancient, and if life arises naturally, then the galaxy should be overflowing with civilizations. So, where is everybody? One radical answer to this profound silence is the zoo hypothesis. This theory proposes a galaxy that is far from empty. It is instead a vibrant galactic community, a cosmic federation of advanced beings who have made a collective, ethical decision. They have designated Earth as a protected wilderness area, a planet-sized nature preserve. Under this strict policy of non-interference, they observe us from a cloaked distance, refusing to make contact until humanity passes some critical test of maturity, perhaps achieving global peace or a sustainable civilization. For decades, mainstream science dismissed this idea as untestable science fiction, an anthropomorphic fantasy that projects our own conservation efforts onto a cosmic scale. How could we ever prove we are being watched by beings who are determined to remain hidden? Yet, the hypothesis forces us to confront uncomfortable questions about our own readiness. Our planet is marked by war, environmental crisis, and technological adolescence. Would any advanced society willingly invite such turbulence into their interstellar community? Perhaps the great filter, the hypothetical barrier that prevents civilizations from reaching the stars, is not a natural catastrophe but a social and ethical one. The very act of looking for external observers compels us to turn the mirror on ourselves. to ask if we are truly a species worthy of a galactic introduction. This concept of a hidden, structured cosmos, operating by rules we have not yet decoded, resonates deeply with a theory that suggests the universe itself is built from tiny, vibrating strings. Einstein's constant C stands as a pillar of modern physics, an unwavering cosmic speed limit. But what if that pillar was once a swinging pendulum? The theory of a variable speed of light dares to suggest that in the universe's first furious moments, light raced across the newborn cosmos at a speed far greater than it does today. This is not a minor adjustment. It is a direct challenge to the very foundation of relativity, which holds the speed of light as the one true constant, the same for all observers for all time. The theory emerged to solve two of cosmology's most stubborn puzzles. The horizon problem asks how regions of the universe on opposite sides of the sky, which could never have been in thermal contact given the age of the universe, manage to reach the exact same temperature. The flatness problem questions why the geometry of our universe is so perfectly balanced, teetering on the knife edge between eternal expansion and eventual collapse. The dominant solution, cosmic inflation, proposes a brief period of faster-than-light expansion to smooth everything out. But João Megiddo and other physicists offered a radical alternative. What if, instead of space stretching unimaginably fast, light itself simply moved faster? In this model, the early universe's inflated horizons were not created by stretching space, but by light's ability to connect distant regions almost instantly, allowing temperature to equalize before the speed of light settled into its modern, slower value. This elegant idea was met with intense resistance. To suggest that c is variable is to tamper with the sacred equations of Einstein, a move many considered scientific blasphemy. Yet proponents argue their theory is not just philosophical rebellion, it is a testable alternative. They predict that a variable speed of light would leave a distinct, subtle signature in the cosmic microwave background, a pattern of fluctuations different from those predicted by inflation. Our most powerful telescopes are now mapping that ancient light with incredible precision, searching for these cosmic fingerprints. The question hanging in the void is profound. Are the fundamental constants of nature truly eternal and unchanging? Or are they merely the current settings of a much more dynamic and evolving cosmos? This challenge to the constancy of light forces us to look closer at the very fabric of the void, the nature of the space through which it travels. Einstein's own work seemed to banish the ether from physics forever. Yet a ghost of this discredited medium still haunts the edges of our understanding. The 19th century concept of the luminiferous ether was a simple and elegant idea, a static, invisible substance filling all of space, a necessary medium for light waves to travel through, much like sound needs air. Then came the Michelson-Morley experiment, a meticulous search for this cosmic wind. By measuring the speed of light in different directions as Earth moved through space, they expected to detect our planet's motion through the stationary ether. They found nothing. The speed of light was constant, utterly unaffected by our direction of travel. This famous null result was a death blow to the classical ether, and paved the way for Einstein's theory of relativity, which needed no such medium. But the story did not end there. In the strange world of quantum mechanics, the idea of a foundational medium has returned in a startling new form. Some theorists now propose that what we call empty space, the vacuum, is not empty at all. It is a dynamic, modern ether, often called the quantum vacuum or the spacetime foam. This is not a static substance but a seething sea of potentiality. According to quantum field theory, the entire universe is permeated by invisible fields. What we perceive as particles, like electrons or quarks, are merely tiny, excited vibrations in their respective fields, like waves on a vast, invisible ocean. The vacuum is the lowest possible energy state of these fields, but it is far from tranquil. Constantly, Pairs of virtual particles and antiparticles flicker into existence for an unimaginably brief moment, borrowing energy from the vacuum before annihilating each other and vanishing back into the void. This is not mere speculation. The Casimir effect, where two metal plates placed extremely close together in a vacuum are pushed together by the pressure of these virtual particles outside them, provides tangible, measurable evidence of this quantum activity. To call this a new ether is deeply controversial, seen by many as a regressive step that betrays the spirit of Einstein's revolution. Yet it offers an intuitive picture of a cosmos where nothing is ever truly empty. It asks a profound question: is the ghost of the ether still with us, not as a substance for light to wave through, but as the fundamental substrate of reality itself, a bubbling quantum foundation from which all matter and energy arise? This concept of a dynamic medium underlying spacetime directly fuels one of the most tantalizing ideas in theoretical physics: the possibility of faster-than-light travel. If space itself is a kind of fabric, then perhaps it can be manipulated, warped, or even engineered, creating shortcuts through the cosmos that bypass the universal speed limit. The ghost of the quantum ether hints at a spacetime that is not a static stage, but a dynamic fabric we might one day learn to weave. This brings us to a concept that transforms faster-than-light travel from science fiction into a mathematical possibility. The Alcubierre warp drive is not about building a faster rocket, but about engineering the very geometry of the universe. Envision a starship not pushing against the void, but sitting motionless within a bubble of distorted spacetime. In front of this bubble, space is compressed, pulling the destination closer. Behind it, space is expanded, pushing the point of origin away. The ship itself rides inside this warp bubble, never accelerating locally, and thus never breaking Einstein's cosmic speed limit within its own reference frame. It is not moving through space faster than light. It is moving space itself. The idea was first rigorously proposed by physicist Miguel Alcubierre in 1994, as a direct solution to the equations of general relativity. For years, it was dismissed as a clever but physically impossible trick, a mathematical curiosity. The central problem was the requirement for exotic matter, a theoretical substance with negative energy density. This is not merely antimatter, but something far stranger, a material that would generate negative gravity, effectively repelling spacetime rather than attracting it. The energy requirements for such a feat were calculated to be astronomical, on the scale of converting the mass of entire planets into pure energy. Yet, the dream refused to die. In recent years, theoretical research has chipped away at these seemingly insurmountable barriers. Scientists have explored different geometries for the warp bubble, suggesting that by shaping the negative energy field in a torus, a ring-like structure, the total amount of exotic matter required could be drastically reduced from a Jupiter-sized mass to perhaps just a few kilograms. While this remains entirely theoretical, and the existence of negative energy is still hotly debated, the very fact that such a reduction is mathematically possible has shifted the warp drive from the realm of pure fantasy to a tantalizing, if distant, frontier of physics. It represents the ultimate expression of human ingenuity, the audacious hope that we might not just live within the laws of physics, but learn to rewrite the local code of spacetime for our own journeys. Could engineering eventually tame the fabric of the cosmos, folding the galaxy into a neighborhood we can traverse within a single lifetime? The very act of manipulating spacetime in this way forces us to ask what other secrets are woven into its hidden structure, perhaps in dimensions beyond our perception. Our three-dimensional world feels like the complete picture, the entire stage for existence. Yet the mathematics of string theory whispers of a grander architecture, a reality built upon not just 3, but perhaps 10 or more spatial dimensions. The extra dimensions are not vast, empty voids like the ones we know. They are thought to be compactified, curled up into shapes so incredibly tiny at the scale of the Planck length that they are completely invisible to our most powerful instruments. This was not just a mathematical curiosity. It offered an elegant solution to one of physics' greatest puzzles, the shocking weakness of gravity. Think about it for a moment. A small refrigerator magnet can defy the gravitational pull of the entire Earth, lifting a paperclip with ease. Why is gravity, the force that shapes galaxies, so feeble compared to the other fundamental forces? The large extra dimensions theory provides a stunning answer. Gravity only seems weak to us because it is not confined to our three-dimensional world. It leaks out, spreading its influence through all the hidden, curled-up dimensions, diluting its strength from our limited perspective. Imagine a puddle on a vast sheet of paper. From the viewpoint of a tiny ant living in the puddle, the water seems to be everywhere. But if the water could seep into the very fibers of the paper, spreading into a third dimension the ant cannot perceive, it would appear to thin out, to weaken from the ant's point of view. For decades, this radical idea was dismissed as untestable speculation, a clever but ultimately fictional escape from the problems of theoretical physics. That changed with the advent of colossal particle colliders like the Large Hadron Collider. If these extra dimensions are real, smashing particles together at nearly the speed of light might provide a fleeting glimpse into this hidden geography. The immense energy of the collision could, for an instant, create particles that are able to move within these tiny dimensions. Scientists search for the telltale signatures of such events, like the sudden, unexplained disappearance of energy, which could indicate that a particle has carried energy away into an unseen dimension. The most dramatic prediction is the creation of microscopic black holes, which would instantly evaporate in a shower of detectable particles. So far, the colliders have found no definitive proof, but the search continues, probing the fabric of reality at ever smaller scales. The question this theory forces upon us is humbling. Is our perception of the universe's fundamental structure merely a consequence of our own dimensional limitations? Are we, in essence, flatlanders unaware of the richer geometry that surrounds us? This search for reality's hidden layers inevitably turns to the one dimension we all experience so directly: the relentless and mysterious flow of time. The relentless forward march of time feels like the most unbreakable law of our existence. But what if this is merely a stubborn illusion, a story we tell ourselves? Retrocausality confronts the bedrock principle that cause must always come before effect, suggesting instead that the future can reach back and shape the past. This idea was not just controversial, it was considered a logical impossibility, a violation of common sense so severe that it was barred from serious scientific debate for decades. The roots of this radical notion lie in the same quantum mysteries that baffled Einstein. Take the phenomenon of quantum entanglement, where two particles become linked across vast distances. If you measure the property of one particle, its partner instantly assumes a corresponding state, no matter how far apart they are. Einstein called this spooky action at a distance, as it seemed to imply information traveling faster than light. Retrocausality offers a startlingly elegant solution. What if the correlation between the particles is not caused by a mysterious signal in the present, but is instead established by the final measurement itself, an event that then propagates its influence backwards through time? In this view, the moment you choose to measure the particle, that decision ripples not only forward, but also backward, setting up the initial conditions that made the entangled link inevitable. It is as if the universe, in its quest for consistency, allows the future to tidy up the past. This does not mean you can change a historical event you already know about. The theory operates on the quantum level, where possibilities are fluid. It proposes that the arrow of time might be a two-way street, with the present moment acting as a negotiation between what has been and what will be. Our choices now could be subtly influenced by goals we have not yet achieved. A constant, silent dialogue across time. This temporal flexibility forces a profound question about the nature of reality itself. Is the universe a story written in stone from the first moment? Or is it a manuscript being edited from the final chapter backwards? This strange possibility that the future is not set in stone leads to a theory about the ultimate destiny of everything, a final state of cosmic perfection. Dark energy's relentless push could lead to a far more violent finale than a slow fade into cold darkness. The Big Rip theory dares to follow the logic of cosmic acceleration to its most terrifying conclusion. It proposes that dark energy is not a constant force but something far more potent, a phantom energy that grows stronger over time. In this scenario, the expansion of space does not merely speed up, it becomes self-amplifying, eventually overwhelming every force that holds the universe together. First, the fabric of spacetime itself would stretch faster than the speed of light, severing the gravitational bonds between galaxy clusters. Billions of years from now, the Milky Way would find itself utterly alone in an ever-darkening void. But the destruction would not stop there. The accelerating expansion would then tear apart individual galaxies, ripping stars from their orbits and flinging them into the endless night. As the phantom energy intensifies, it would next target solar systems, pulling planets away from their suns. In the final, horrifying moments, the very forces that bind matter together would fail. The fabric of spacetime would stretch at an infinite rate, shredding planets, then molecules, and finally atoms and atomic nuclei themselves. Every last bit of structure in the cosmos would be vaporized into a soup of disconnected fundamental particles, unable to ever interact again. This is not a heat death. It is a cosmic execution. The key to this apocalyptic fate lies in a specific property of dark energy called its equation of state parameter. If this value is less than -1, the Big Rip becomes not just a possibility, but an inevitability. Current observations cannot yet rule this out, leaving the most violent end to reality still on the table. The question this theory forces upon us is stark. Does the universe end with a whimper, or with a scream that tears apart the very fabric of reality? This vision of ultimate disintegration clashes profoundly with a principle that claims something in the universe is truly eternal. A black hole is a paradox given cosmic form. It presents physics with an impossible choice between its two greatest triumphs. On one hand, quantum mechanics insists that information, the detailed identity of every particle, can never be truly destroyed. It can be scrambled, transformed, but never erased from the universe. This is a fundamental tenet of reality's memory. On the other hand, general relativity describes a black hole as a region of spacetime so warped that nothing, not even light, can escape its gravitational grip. Anything crossing the event horizon, the point of no return, is lost to the universe forever. So what happens to the information describing a book, or a star, or a person that falls into a black hole? Is it preserved, or is it obliterated? For a long time, the great Stephen Hawking argued for the latter. He calculated that black holes are not perfectly black. They slowly evaporate over eons by emitting a faint glow of radiation. But this Hawking radiation, he claimed, is entirely random, carrying no information whatsoever about what fell in. When the black hole finally vanishes, all the information it ever consumed would be erased from existence. This conclusion, known as the information paradox, sent shockwaves through the theoretical world. It meant our understanding of physics was fundamentally flawed, that one of our core theories must break down at the precipice of a black hole. The scientific community was deeply divided. Accepting Hawking's idea meant rewriting the laws of quantum mechanics. Rejecting it meant finding a flaw in the impeccable logic of general relativity. The search for a solution led to one of the most profound ideas in modern physics, the holographic principle. Perhaps the information is not lost inside the black hole because it was never truly there to begin with. Instead, it is encoded, pixel by pixel, on the two-dimensional surface of the event horizon like a cosmic hard drive. The three-dimensional interior we imagine is just a projection, a shadow of that encoded data. This resolves the paradox by suggesting that information never actually crosses the horizon. It is smeared across it, permanently saved from destruction. The debate forced physicists to confront the very nature of reality. Is the universe fundamentally a place of things, or is it a place of information? The struggle to preserve information against cosmic oblivion hints at a deeper, more beautiful order, a principle of symmetry that might govern every interaction in the cosmos. Symmetry is the silent architect of reality, a deep and pervasive order that governs everything from the spirals of galaxies to the structure of atoms. Yet for all its elegance, our current model of particle physics contains a glaring asymmetry. The universe is built from two distinct families of fundamental particles, matter particles like electrons and quarks, and force-carrying particles like photons. Supersymmetry dares to propose a breathtakingly beautiful solution, a hidden symmetry so profound it would unite these two families into a single, cohesive whole. The theory suggests that for every known particle in existence, there is a massive, undiscovered superpartner. An electron would be paired with a selectron, a quark with a squark, and a photon with a photino. This elegant doubling of the cosmic roster was not dreamed up for mere aesthetic pleasure. It solves one of physics' most nagging problems, the hierarchy problem. This is the puzzling question of why the force of gravity is so unimaginably weaker than the other fundamental forces. The math of our standard models suggests that the mass of the Higgs boson, the particle that gives others their mass, should be driven to an astronomically high value by quantum fluctuations, making our universe impossible. Supersymmetry elegantly cancels out these fluctuations, stabilizing the Higgs mass and making a life-permitting cosmos mathematically plausible. Furthermore, the lightest of these superpartners is a perfect candidate for the mysterious substance we call dark matter, an invisible particle that just floats through ordinary matter without interacting. For decades, supersymmetry was the leading hope for a theory of everything, a bridge to a deeper, more complete understanding. Then came the Large Hadron Collider. This monumental machine was built in part to discover these superpartners. It found the Higgs boson, a triumphant confirmation of the Standard Model, but it found no selectrons, no squarks, no photinos. The beautiful symmetry remained stubbornly hidden. The failure to detect any sign of supersymmetry at the energy scales we can probe has cast a long shadow over the theory. What was once a darling of theoretical physics is now viewed with increasing skepticism, with major journals becoming reluctant to publish new speculative papers on the subject. The question now is whether this beautiful idea is simply wrong, or if the superpartners are so immensely heavy that they exist at energy scales far beyond our current reach, hiding in realms we cannot yet explore. The dream of supersymmetry confronts a difficult reality, that nature may not always conform to our human sense of mathematical beauty. This search for a hidden order in the particle zoo inevitably leads us to question the nature of the stage they perform upon, the very essence of empty space. Quantum mechanics insists the world is fundamentally random, a game of probability where particles exist as clouds of possibility until observed. But there is another path, one that restores a sense of order to the subatomic realm. Pilot wave theory dares to propose that particles are not fuzzy probability clouds, but real, tangible objects with definite positions and trajectories at every single moment. In this view, every electron is a tiny corpuscle, a real point-like particle, but it is not alone. It is guided by a hidden wave, a pilot wave that moves through space, shaping the particle's path. Think of a cork bobbing on the surface of a turbulent river. The cork has a real position at all times, but its movement is entirely determined by the complex waves and currents flowing around it. The particle is the cork, and the pilot wave is the river. This idea, first proposed by Louis de Broglie and later developed by David Bohm, offers a completely deterministic interpretation of quantum mechanics. It eliminates the need for a conscious observer to collapse the wave function, because the wave and the particle always exist together. The famous probabilistic nature of quantum events, like an electron appearing in one spot or another, is not due to inherent randomness. It arises from our ignorance of the exact initial conditions of the pilot wave. Much like not knowing the exact swirls in a river current makes a cork's final resting place seem random. For decades, this theory was aggressively marginalized by the physics community. The dominant Copenhagen interpretation, with its embrace of probability and the central role of measurement, became the orthodox view. Pilot wave theory was dismissed as a regression to outdated classical thinking, an attempt to put the genie of quantum weirdness back into a deterministic bottle. It was considered too clunky, too contrived, and its non-local nature, where the pilot wave instantly influences the particle regardless of distance, was seen as a fatal flaw. Yet, a remarkable series of experiments has breathed new life into this once banished idea. In a laboratory tray, researchers have created a macroscopic analog using a vibrating fluid. A tiny droplet of oil can bounce on the surface of the liquid, propelled by its own waves. This walking droplet exhibits behaviors uncannily like quantum particles, from tunneling through barriers to creating interference patterns, all while having a perfectly definite trajectory. This suggests that quantum strangeness might not be a property of the particles themselves, but an emergent property of a deeper, hidden dynamics. The question this revival forces upon us is profound. Have we been wrong about quantum mechanics all along? Is the universe fundamentally deterministic after all? Its apparent randomness merely a veil over a reality we have not yet learned to see. This challenge to quantum randomness stands in stark opposition to a theory that embraces chance as the very engine of existence. The quantum world's refusal to settle on a single outcome forces a radical possibility. What if every possibility actually happens, just not in our reality? The many worlds interpretation proposed by physicist Hugh Everett offers a breathtakingly audacious answer. It suggests that the universe does not choose. Instead, at every moment of quantum uncertainty, the entire cosmos splits. For every possible outcome, a new, fully real universe branches away from the old one, each one containing a version of events where a different possibility became real. This is not a metaphor. It is a direct interpretation of the same mathematical equations that underpin all of quantum mechanics. Everett's genius was to take the wave function, the description of a particle's probability cloud, completely seriously. He argued it never collapses. It simply continues to evolve, and the appearance of collapse from our perspective is just our consciousness following one thread in an endlessly branching tapestry of reality. The appeal is profound simplicity. This interpretation neatly eliminates the need for a mysterious observer to cause the collapse, sidestepping one of quantum theory's most perplexing problems. Yet this simplicity comes at an almost unimaginable cost. It means that right now, a universe exists where you never clicked on this video, another where dinosaurs still roam the Earth, another where the very laws of physics are different. Every choice, every random quantum event, spawns a new cosmos. Hugh Everett's thesis was met with silence and then derision. The physics community, led by the influential Niels Bohr, dismissed it as ontologically extravagant, a fancy way of saying it proposed far too many unobservable realities to be taken seriously. It was brushed aside for decades, a solution considered worse than the problem it solved. But the idea refused to die because it forces a deeply personal question. In this infinite multiverse, there are countless versions of you. Some are living lives of unimaginable joy and success, while others endure every conceivable hardship. Are you the lucky one? Or is there a version of you out there who would consider your life the lucky one? This concept of a branching, fractal cosmos challenges our sense of uniqueness, suggesting our path is just one thread in an infinite tapestry. And if our universe is part of an unfathomably vast multiverse, it forces us to ask what binds this cosmic structure together on the very largest scales. The infinite branching of the quantum multiverse is a story of moments, a fractal splintering of possibility. But there exists a vision of multiplicity on an even grander scale, a multiverse of worlds, not just choices. This is the cosmological multiverse, a concept born from the dominant theory of our universe's birth, cosmic inflation. Here, our Big Bang was not a unique, singular event. It was merely one bubble in a vast, eternal cosmic foam. In this eternal inflation, the fabric of spacetime is constantly stretching at an exponential rate. But this expansion is not perfectly uniform. Like a pot of water coming to a boil, tiny quantum fluctuations can trigger the formation of new bubbles. Each one is a pocket universe, pinching off from the inflating background and expanding into its own cosmos, complete with its own Big Bang and, crucially, its own random set of physical laws and constants. In one bubble universe, gravity might be repulsive, preventing planets from ever forming. In another, the strong nuclear force could be too weak for atomic nuclei to hold together, leaving no possibility for stars or chemistry. Our universe, with its seemingly perfect fine-tuning for life, is not a miracle. It is simply a statistical inevitability. If you have an infinite number of universes, every possible combination of physical parameters will occur somewhere. We do not live in a special cosmos. We just happen to inhabit one of the rare bubbles where the numbers lined up correctly for galaxies, stars, and life to emerge. For many scientists, this is a deeply troubling idea. It seems to render the scientific quest for a single, elegant theory of everything potentially futile. Why search for a fundamental reason why the electron has its specific mass, if that value is just a random draw in our particular cosmic lottery? Critics argue that because these other universes are, by definition, beyond our observational reach, the entire concept is not falsifiable and therefore not science, but metaphysics. Yet its explanatory power is undeniable. It offers a natural, physical mechanism for the Anthropic Principle, turning a philosophical puzzle into a potential prediction of a leading cosmological model. This vast perspective forces a humbling realization. Our entire reality, with all its beauty and complexity, might be nothing more than a fortunate accident in an endless ocean of silent, lifeless universes. In such an immense and disconnected cosmos, the idea of a fundamental, instantaneous connection between all things seems almost miraculous. Einstein's own phrase, spooky action at a distance, perfectly captures the deep unease this phenomenon provoked. Two particles become linked, entangled, so that measuring the state of one instantly determines the state of the other, even if they are separated by the width of a galaxy. For Einstein, this was not a triumph of quantum theory but proof of its absurdity. He argued it violated the cosmic speed limit set by his own theory of relativity, the idea that no information can travel faster than light. He insisted there must be hidden variables, unseen mechanisms that predetermine the particle's states, preserving a classical, local reality where influences travel smoothly through space and time. For decades, this remained a philosophical debate, a clash of interpretations. Then came a physicist named John Bell. He devised a mathematical test, now known as Bell's theorem, which could determine whether these hidden variables could possibly exist or if the universe was truly as spooky as it seemed. When laboratories around the world finally performed these delicate experiments, the results were unequivocal. The particles were connected in a way that defied any local, hidden variable explanation. The correlation was instantaneous, a silent communication that seemed to bypass the fabric of spacetime entirely. This non-locality suggests that at its most fundamental level, the universe is not a collection of separate, isolated objects. Instead, it is a deeply interconnected whole, where the idea of true separateness may be an illusion born from our limited perception. If two particles can be instantly linked across cosmic distances, what does that say about the space between them? Is space itself not a barrier, but a kind of projection? This radical interconnectedness is the bedrock of a startling idea, that the cosmos might not be a place at all, but a process, a colossal computation unfolding according to a set of fundamental rules. This profound interconnectedness suggests a cosmos that operates less like a collection of separate objects and more like a unified, dynamic process. Perhaps the universe is not just governed by laws, but is actively processing information on a cosmic scale. This is the radical proposal that the universe itself is a quantum computer. Instead of particles and forces being the fundamental building blocks, they are the outputs of an ongoing, unimaginably complex computation. The laws of physics we have discovered are not merely descriptive rules. They are the operating system, the algorithms this cosmic computer is running. Every collision of particles, every orbit of a planet, every flicker of a star is a step in a calculation. The pioneering physicist John Wheeler captured this idea with the phrase "it from bit," suggesting that every particle and force ultimately derives from a bit, a unit of information. This was not a metaphor for Wheeler, but a serious hypothesis about the nature of reality. For decades, this was considered pure philosophy, far too speculative for rigorous science. How could one possibly test such an idea? Yet, it emerges naturally from the digital physics movement, which posits that information is the most fundamental substance of existence, more basic than energy or matter. If this is true, then the universe is not a thing that contains information. It is information that has taken the form of a thing. The question then becomes staggering in its implication. What is the universe computing? Is it calculating its own evolution, solving the equation of itself? And if it is a computation, does that imply a programmer, an initial input of code that set the whole process in motion? This view transforms reality into a cosmic question. It suggests that at its heart, existence might be fundamentally mathematical, a structure of logical relationships waiting to be decoded. This computational perspective forces a radical rethinking of our most basic experience, the relentless flow of time. If the universe is a computer, then time might not be a fundamental river, but simply the sequence of processing cycles, an emergent property of the computation itself. The smooth stage of space and time we take for granted might be nothing more than a convincing collective illusion. The theory of emergent spacetime proposes that the universe's fundamental fabric is not a continuous sheet but a tapestry woven from countless invisible threads. According to this radical view, spacetime is not a primary ingredient of reality. It is an emergent property, a large-scale effect that arises from the interactions of something far more basic, just as the wetness of water emerges from the collective behavior of individual molecules. This idea was long dismissed as a fringe speculation because it dismantles the very foundation of Einstein's general relativity, which treats spacetime as a dynamic but smooth continuum. The key to this emergence appears to be quantum entanglement, that same spooky connection that links particles across vast distances. Physicists now suspect that the geometric structure of space itself, the distance between 2 points, might be built from a vast, complex web of entangled quantum bonds. The more entangled two systems are, the closer they are in spacetime. This turns our intuition inside out. We do not live in a container called space where entanglement happens. Instead, our experience of space is a consequence of entanglement. The implications are staggering. If space-time is not fundamental, then the Big Bang singularity, that point of infinite density from which everything supposedly exploded, might not be a true beginning. It could represent a phase transition, like water freezing into ice, where the properties of the cosmos changed dramatically as space-time itself crystallized from a more primitive, non-spatial state. This forces a profound question. If space and time are not the bedrock of existence, what is the true fundamental substance of the cosmos? Are we, and everything we perceive, simply patterns in a deeper, spaceless, timeless quantum reality? This bottom-up view of a cosmos built from simple connections contrasts sharply with a theory that takes a top-down approach to the most complex system we know: life itself. Life's presence on Earth has long been framed as a cosmic fluke, a one in a trillion alignment of perfect conditions. But what if we have the story entirely backwards? The theory of cosmic biology dares to propose that life is not a fragile miracle, but a cosmic imperative, an inevitable outcome of the universe's fundamental laws, as predictable as gravity pulling matter into stars. In this view, the emergence of biology from chemistry is not a random chemical lottery win on a lucky planet. It is a natural, law-like process waiting to happen wherever the universe provides a suitable environment and enough time. This idea was heavily criticized for what many saw as unwarranted optimism, a leap of faith that replaced careful science with a hopeful narrative. Its proponents, however, point to the vastness of cosmological timescales. Over billions of years on countless worlds, the complex dance of atoms and energy is not just likely to stumble upon self-replication, it is almost statistically guaranteed. The building blocks are everywhere. We have found the precursors to life, complex organic molecules like amino acids and sugars, floating in the vast clouds of gas between the stars, on asteroids, and in the atmospheres of distant planets. These are not the seeds of life themselves, but the cosmic alphabet from which life's language can be written. If the letters are scattered across the galaxy, is it so surprising that on some worlds, they eventually form words, then sentences, then entire stories? This perspective transforms life from a passive accident to an active, driving force in cosmic evolution. It suggests that the universe is inherently bio-friendly, its physical constants and chemical richness predisposed to give rise to living, evolving systems. If life is indeed written into the laws of physics, then the silent cosmos we perceive may not be empty at all, but quietly humming with biological activity, a garden at the very beginning of its bloom. This vision of life as a fundamental cosmic process inevitably leads us to wonder what such life might eventually become. The moment an intelligence surpasses our own may be the last event in human history that we truly understand. This is the core of the technological singularity, a point on the horizon where artificial intelligence begins to recursively improve itself, triggering an explosion of technological growth that becomes uncontrollable and irreversible. For decades, this was a fringe concept, the domain of science fiction writers and a few bold futurists like Ray Kurzweil. It was dismissed as alarmist fantasy, a digital doomsday scenario that ignored the practical limitations of computing. But the exponential curve of progress has a way of catching up with skepticism. With the recent breathtaking leaps in artificial intelligence, from mastering complex games to generating human-like text and art, the singularity is no longer a distant philosophical curiosity. It is a plausible, and for some, an imminent future. The central fear is not of malevolent robots, but of a fundamental disconnect in understanding. A superintelligence would not simply be a faster human brain. Its goals and thought processes might be as incomprehensible to us as human morality is to an ant. This creates an event horizon for prediction, a point beyond which the future of civilization, and even the definition of intelligence itself, becomes a complete mystery. The critical ethical question is not if we can build such an entity, but whether we can instill it with a value system that ensures our survival and flourishing. Would a superintelligence see humanity as a cherished predecessor, a useful tool, or an inefficient relic consuming valuable resources? The singularity forces us to confront the possibility that our greatest invention could also be our final one, an intelligence that either transcends our limitations or renders us utterly obsolete. This profound uncertainty about the future of mind inevitably draws our gaze backwards, to the silent eons of our own past, and to the possibility that another intelligence may have already walked this path. The silence of the cosmos is broken only by the monumental achievements of our own ancestors. How did ancient civilizations with only stone tools and human labor construct wonders that still baffle our modern engineers? The theory of ancient astronauts proposes a radical answer, that these feats were not solely human accomplishments, but the result of contact with extraterrestrial visitors in our distant past. Erich von Däniken became the most famous proponent of this idea, suggesting that the gods and heroes of ancient myths were not divine beings but advanced aliens whose technology was mistaken for magic. He pointed to the precise stonework of the pyramids, the massive Nazca lines in Peru visible only from the sky, and intricate descriptions of flying chariots in ancient texts as potential evidence of this otherworldly intervention. Mainstream archaeology and science reacted with fierce rejection. They argued that this theory was not just wrong, but deeply disrespectful, robbing our ancestors of their ingenuity and creativity by attributing their greatest works to outside help. The lack of any physical evidence, like an alien tool or a piece of starship wreckage, made the claims impossible to verify, relegating them to the fringes of pseudoscience. Yet, the core question it raises is more durable than any specific claim. If an advanced civilization did visit Earth 10,000 years ago, what traces would remain after centuries of erosion, geological shifts, and the rise and fall of countless human cultures? A soda can left on a prehistoric riverbank would have corroded into dust long ago. The very concept of evidence changes when stretched across such vast timescales. This forces a humbling possibility. Our entire understanding of human history is built upon a fragmentary archaeological record, a collection of clues that survived by chance. Could we be misinterpreting the most important chapter of our own story because we are looking for the wrong kind of proof? This search for lost cosmic contact shifts the focus from our distant past to our immediate celestial neighborhood, to the possibility of finding alien artifacts not buried on Earth, but waiting for us on the Moon, on Mars, or drifting silently through the asteroid belt. The silent monuments of our own past stand as a challenge, but the search for alien intelligence may require looking for relics far older and more distant. This is the quest of SETA, the search for extraterrestrial artifacts, a field that dares to ask a simple but profound question. If a civilization truly became interstellar, would it not leave something behind? Instead of listening for fleeting radio whispers, SETA proponents scan the solar system for physical evidence, for the derelict probes, abandoned outposts, or industrial remnants that a spacefaring culture might have left in its wake. The logic is compelling. A functioning beacon requires constant power and maintenance over millennia, but a silent, dormant artifact could survive for eons, waiting to be discovered. Imagine a Voyager-like probe, but on a million-year journey, drifting in the frozen depths of the Kuiper Belt. Or consider the possibility of automated mining operations on resource-rich asteroids, their work long since completed, leaving behind only strangely geometric scars on the rock. Even Mars, a world with a potentially habitable past, could hold the ruins of a base buried beneath the red dust, a testament to a visit that occurred before humanity ever walked the Earth. For decades, this approach was dismissed as the ultimate needle in a haystack problem, a fringe pursuit with probabilities so vanishingly small it was not worth serious scientific consideration. How could we possibly find one ancient object in the unimaginable vastness of our own cosmic backyard? Then came Oumuamua. In 2017, our telescopes detected an object unlike any other, tumbling through our solar system on a trajectory that confirmed it was a visitor from interstellar space. Its elongated shape, unusual acceleration, and lack of a visible cometary tail sparked intense debate. While most scientists concluded it was a natural object, a few dared to voice the possibility that Oumuamua's strange properties were consistent with a light sail or a derelict spacecraft. The controversy highlighted the core challenge of SETA. How do we distinguish a natural oddity from an artificial one when we have only one example of each to compare? The very act of looking forces a shift in perspective, turning every unusual crater on the Moon, every oddly shaped asteroid, into a potential site for astroarchaeology. This tangible hunt for cosmic ruins connects to a far more abstract mystery. If we ever did find such an artifact, its very existence would challenge our understanding of reality, suggesting that the laws of physics as we know them might not be the final word, but merely a local set of rules that a more advanced intelligence had learned to engineer. The bedrock of science is the belief that the rules of the game never change. We assume an electron has always had the same charge and gravity the same pull, from the first instant after the Big Bang to this very moment. But this assumption of constancy may be the grandest illusion of all. The laws of physics themselves could be evolving, slowly changing over cosmic time. This idea was scientific heresy, a direct challenge to the principle that allows us to trust any experiment or observation. If the rules are in flux, how can we ever hope to understand the universe's past or predict its future? Yet, a few brave cosmologists dared to ask what if the fine structure constant, a number that governs the strength of electromagnetic interactions, is not so constant after all. By analyzing the faint light from quasars billions of light years away, they are effectively looking back in time, searching for tiny shifts in the spectral fingerprints of distant atoms. A detected variation would be a seismic event in physics. It would mean the universe of 10 billion years ago operated under a slightly different set of rules than the one we measure today. Our entire understanding of reality would become provincial, a snapshot of local physics, not a universal truth. This transforms the cosmos from a static rulebook into a dynamic learning system. If the laws can change, then the question of where they came from becomes even more urgent, pointing toward a moment of pure potentiality, a beginning from absolute nothing. The ultimate question has haunted philosophy and science for millennia. Why is there something rather than nothing at all? The idea that our entire universe could have simply popped into existence from a state of absolute nothingness was long considered the final frontier of metaphysics, a question science could never hope to answer. It was the ultimate untestable speculation. Yet, a radical theory dared to bring this question into the realm of physics, proposing that the universe is its own reason for being, requiring no external cause. This concept hinges on a subtle but profound redefinition of nothing. In our everyday experience, nothing is an empty box, a void. But in quantum physics, a perfect vacuum is not truly empty. It is a seething sea of potential, where pairs of virtual particles constantly flicker in and out of existence, borrowing energy from the void for an infinitesimally brief moment. Physicists like Lawrence Krauss have argued that if this quantum vacuum is unstable, then a fluctuation on a cosmic scale is not just possible, but inevitable. Given an infinite amount of time, or a pre-existing quantum state, a fluctuation large enough to birth an entire universe becomes a statistical certainty. The universe, in this view, is the ultimate free lunch, This idea elegantly sidesteps the need for a creator, suggesting that the laws of physics themselves are sufficient to bring everything into being from nothing. But this solution immediately raises a deeper, more troubling question. Where did the quantum laws come from? Why do these specific rules exist that allow something to emerge from nothing? If the laws are a prerequisite for the universe's existence, then they themselves seem to be a form of something, a pre-existing framework. This pushes the mystery of origins back one step further, into a realm that may forever lie beyond scientific inquiry. Can science truly explain existence, or does it eventually hit a wall where only philosophy or faith can venture? This theory does not provide a final answer, but it transforms the question from a philosophical puzzle into a physical one, forcing us to confront the bizarre possibility that nothingness is inherently unstable, and that existence is the natural, inevitable result. This contemplation of a self-creating cosmos finds a strange echo in a theory that suggests the entire universe is bound together by an invisible web of connection, linking the largest scales to the smallest. The universe reveals a startling secret when you shift your perspective. Zoom out to the grand tapestry of galaxy clusters, and you see vast, web-like filaments connecting immense nodes of matter. Now, zoom in on the microscopic structure of a fragment of rock, and you might see a similar pattern of interconnected networks. This eerie resemblance is the heart of the theory of scale invariance, which dares to suggest our cosmos is a fractal. In a fractal universe, there is no single, true scale. The same basic patterns repeat themselves from the largest superclusters down to the tiniest quantum fluctuations. A single galaxy looks like a miniature version of the entire cosmic web. This idea directly confronts one of the foundational pillars of modern cosmology, the cosmological principle, which states that on the largest scales, the universe is smooth and homogeneous, meaning it looks the same in every direction. The fractal theory proposes the opposite, that the universe is inherently lumpy and self-similar at every level of magnification. For decades, this was considered a mathematical curiosity with no basis in reality, dismissed because it seemed to contradict the overwhelming evidence of the cosmic microwave background, the afterglow of the Big Bang, which appears incredibly uniform. But the story is more complex. When astronomers map the three-dimensional positions of millions of galaxies, they do not see a perfectly smooth soup. They see a complex, hierarchical structure, with galaxies grouped into clusters, clusters into superclusters, and superclusters into immense filaments that stretch across billions of light years, surrounding vast, empty voids. Some analyses suggest this fractal-like pattern holds true across a staggering range of scales. The implication is profound. A fractal cosmos is a deeply connected one, where the same organizing principles govern the birth of a star and the spin of a galaxy. It hints at a universe built not from separate, isolated objects, but from a single, recursive process of creation, echoing its own design from the quantum realm to the cosmic horizon. This relentless search for a hidden pattern, a unifying symmetry behind the chaos of existence, pushes us toward the ultimate question about the nature of discovery itself. The relentless search for a hidden pattern, a unifying symmetry behind the chaos of existence, pushes us toward the ultimate question about the nature of discovery itself. The final band theory strikes at the very heart of the scientific enterprise. It dares to ask if the physical world is all there is. Post-materialist science confronts the most stubborn mystery of all, the hard problem of consciousness. How do 3 pounds of gelatinous tissue inside your skull generate the rich, inner universe of your thoughts, your feelings, your very sense of self? Materialism, the foundational philosophy of modern science, insists that consciousness is merely an emergent property of the brain, a complex chemical byproduct. Yet this leaves the how completely unexplained. Why should any specific arrangement of atoms feel like anything at all? Proponents of a post-materialist view argue that consciousness might not be produced by the brain, but rather received by it, like a radio tuning into a broadcast. They point to documented near-death experiences, where individuals report lucid, verifiable perceptions occurring during periods of clinical brain death, when no neural activity should be possible. They cite decades of controversial psi research into phenomena like telepathy or precognition, results that, while statistically faint and fiercely debated, suggest the mind might interact with the world in ways that defy purely physical models. For mainstream journals, this was the ultimate heresy. To suggest that mind could be as fundamental as matter, or even more so, was to abandon the core principle that has guided science for centuries. It was seen as a slippery slope back to superstition and mysticism, but the question remains profound. By insisting that only physical explanations are valid, has science placed a filter on reality, blinding itself to entire dimensions of existence? Is our current scientific framework simply not equipped to study consciousness because it begins by assuming consciousness is not real in its own right? The suppression of these 33 theories is not merely a historical curiosity. It is a cautionary tale about the power of orthodoxy. Each banned idea represented a path not taken, a question that was silenced before it could be fully explored. The cost of this censorship is immeasurable. It is the cost of lost time, of delayed revolutions, of a scientific narrative that may be narrower and less true than it could have been. The true lesson is not that every banned theory was correct, but that the process of banning itself is a dangerous failure of curiosity. Science, at its best, is not a fortress defending a body of knowledge. It is an endless frontier, a perpetual state of questioning. The most radical idea of all may be that to truly understand the cosmos, we must first have the courage to question the unquestionable foundations of our own methods. The silence imposed on radical ideas carries a profound collective cost, a debt paid not in currency but in lost time and stifled progress. The history of science is a graveyard of theories once mocked that later proved foundational. Alfred Wegener's continental drift was dismissed as fantasy for decades before plate tectonics revolutionized geology. Ignaz Semmelweis was ridiculed for suggesting doctors should wash their hands, a simple truth that could have saved countless lives. Each suppression creates a lag, a period where humanity remains in the dark simply because the light was deemed too bright, too dangerous to behold. This delay is more than an academic inconvenience, it is a brake on our collective evolution. Pioneers are forced to work in isolation, their insights languishing without the oxygen of peer review and collaborative refinement. Worse yet, a culture of conformity takes root, where the safest career move is to align with the consensus, not to challenge it. Young researchers quickly learn that questioning established pillars is a professional risk, a fast track to being marginalized. The central question is not whether every banned theory holds the key to reality. Many will inevitably be wrong. The deeper issue is whether the very act of banning is a betrayal of the scientific spirit. Does a system that prioritizes protecting its core beliefs from heretics truly serve the pursuit of truth, or does it merely protect its own authority? When the fear of being wrong outweighs the courage to explore, we risk building a fortress of knowledge that is sturdy, but permanently incomplete. This reflection on the dangers of dogma leads us to a final, crucial thought about the nature of discovery itself. Our journey through these 33 radical visions reveals a cosmos far stranger and more wonderful than any single theory could contain. From the electric currents sculpting galaxies to the possibility that our reality is a holographic projection, each banned idea represents a door that was once closed, a path of inquiry that was blocked by the very institutions meant to foster discovery. Their collective story is a powerful reminder that science is not a dusty encyclopedia of settled facts. It is a living, breathing, and often contentious conversation, a dynamic process where today's certainty is tomorrow's historical footnote. The true engine of progress has never been blind obedience to authority, but the courageous act of questioning, of daring to ask what if when everyone else insists it cannot be so. Let these theories stand as a testament to the power of an inquisitive mind. They challenge us not to accept every fringe idea, but to cultivate a healthy skepticism toward all claims,